So now I'd like to solve some integration problems, bearing in mind that we have this new rule for integrals that says when we have an integral of the form 1 over u times du, the antiderivative is the natural log of the absolute value of u plus c. So in this first example, the integral of 3 over x dx. In this case, if we just toss that 3 out front, so that's a constant coefficient, we're always allowed to bump those out front, then you're left with 1 over x dx. And remember, with any of these integral problems, the task is just to find a function whose derivative is blank. Well, we just learned about a function whose derivative is 1 over x, and that's natural log of x. So this is equal to 3 times the natural log of, technically if we're going by that rule, absolute value of x. Not dx, plus c. We drop the dx when we take the antiderivative. So one thing about the absolute value, if you consider the domain of this original integrand here, it's all x values not equal to 0. When we write the antiderivative here, with the absolute value, that means that this is also defined for all x not equal to 0. So we have agreement in the domain of our original function and then in the antiderivative. One other thing with this, so this would be fine. This is a good final answer. For when you're checking your answer, just in case you see this kind of thing, keep in mind that constant coefficients like this, because of those properties of logarithms, this can be, if you want, bumped up into the exponent. So you could express this as natural log of the absolute value of x cubed. You don't have to, let me just say for the record. But when you have an answer in this form, just know you could fold that constant coefficient up into the exponent if you want to. Okay, but overall idea with that first example is just move the 3 out. Antiderivative of 1 over x is natural log of the absolute value of x. With this second example, so it didn't fall into our laps quite as nicely as it did in example 1. But if we apply a substitution, so if we say, yeah, well, this looks roughly like an integral of the form 1 over u du, where u is equal to this expression right here. So if we let u equal x minus 8, then the differential is the derivative of that expression, which is just 1 times dx. So this is one of those cases where du is just equal to dx. And so this becomes the integral of 7 over u, x minus 8, times dx, which is equal to du. We've got an integral completely in terms of u. The 7 can be bumped outside, and then we have exactly 1 over u du. And so the antiderivative is the natural log of the absolute value of u, which I'm going to go ahead and plug back in, is x minus 8. And so here is your answer to this second example, where here again you could write this as natural log of absolute value of x minus 8 to the 7th power if you want. You don't have to. So now we're through example 2. Let's look at this third example. So again, maybe you start to feel like, yeah, I think I can write that in the form 1 over u du. This is the overall rule that we've been using. In this case, u would be 3x minus 5. So du equals the derivative of that, which is 3 times dx. So in this case, if you divide both sides by 3, you have 1/3 du equals dx. And we want to do that because we see, all right, once I do a replacement, turn this into u, then all I have left is dx. So that would be our indication that, okay, well then maybe I'd like to solve for dx in this differential equation by dividing both sides by 3. So that when you write this thing in terms of u, you have 1 over u and dx is equal to 1/3 du. Bump that 1/3 outside. So this is equal to 1/3 times the integral of 1/u du. So this is equal to 1/3 times the natural log of the absolute value of u plus c, where u is 3x minus 5. Now, here, I'll box that up. This is a perfectly acceptable answer, in my view. You could move that 1/3 to the exponent, and if you do, you might remember that the 1/3 power, that's equivalent to the cube root. And again, I'm only mentioning that because, oops, close the absolute value. If you arrive at this for your final answer, and let's say you're checking answers and you see something like this, that might really concern you. But I want you to rest assured that that would be the same thing if you apply that rule for, or that property of logarithms. All right, so there's your answer for example 3. I know we're kind of charging through these. But one last example. So what if you have 1/x minus 5 squared, all squared? You may start out thinking, all right, I'm going to take the same approach. I see a pattern here. I'm going to let u equal. Now, what you let u equal is important. I'm hoping that most of you guys would choose to let u equal x minus 5, which means du is equal to the derivative of that. So that's 1 times dx. So the dx here is just directly equal to du. And this becomes the integral of 1/u squared times du. Now, noticing the squared here is really important. So this is not 1/u times du. This is not an integral of this form this time. If you have something other than 1/u to the first, so like in this case 1/u squared, you should find the antiderivative using power rule. This rule only applies when it's 1/u to the first power. So if you have 1 over square root of u, which is u to the 1/2, or 1/u to the second, or 1/u cubed, you should just use the power rule to integrate that. So express it as u to the -2, apply the power rule. So when you add 1 to the exponent, you get -1, 1 over -1 out front. So that coefficient is -1, u to the -1, so that's 1/u, where u is x minus 5. So this is -1/x minus 5 plus c. The answer here is not a natural log function because this integral does not have the form 1/u du. This one did 1/u, where u is 3x minus 5. This one did 1/u, where u is x minus 8, and this one's just 1/x. So the first three do have the form 1/u du. The third one, or the fourth one, does not. And it's just important, don't get too hooked on this particular rule for integration and forget that in most cases when you have an expression in the denominator, you should just write it as a negative exponent and apply the power rule.